I am going to explain the SP11 circuit from the subproject SP1.1. As you can see, there is a chip that has 3 inputs and 2 outputs, and if we check it inside, there are a lot of logic gates that form this chip. As you can see, there are the inputs, the outputs, and the logic gates. With this chip, we can extract the truth table and the equations, like this one or this one. This is the output D and this is output E. We can check, for example, output E in the Wolfram alpha. Let's see. And as you can see, there is a truth table and there are the outputs and the combinations. Let's check some combinations, like this one, for example. If A is 0, B and C 1, it will be 1, 0, 1, 1, and E, as you can see, is 1. We can check another one, for example, this one. 0, 0, 1 will be 0. 0, 0, 1, and that's 0. It works perfectly with G too, and that's all.
In this lab session, we have to work on circuit SP1, that is this circuit, and it's another 1 bit. First of all, we modified the circuit WVHD from Dixis, and we obtained this file that shows us the logic equations of our circuit and provides with quarters the RTL viewer that shows all the logic gates and the technology map view of our circuit. Then we have modified the circuit W test bench from Dixis 2, and we get this file. So in here we have all the inputs of the truth table, and when we compile this to quarters, we can get the timing diagram that shows how the circuit works. So if we input, for example, 001, we have a 1 and 0 in the carry. And if we input 011, we have a 0 and a 1 in the carry. And this is how the circuit works.
So let's continue with project SP13, in which we confine the circuit alert to bit. We have developed 2 plans. I will start with plan A. First, I'm going to show the Quartus Prime project of alert to bit. Here we have the VHD file, and we can see the code. These are the inputs and the outputs, and the code that we made to make the project. Now I'm going to show the RTL viewer of the circuit, and I will continue with technology map viewer. So we will continue with the test bench of alert2bit. This is the code. Here we have the inputs and the outputs. From the truth table, we have wrote this. As you can see, we have input, first of all, just zeros, and then we continue with the truth table till the end. To see the results of this circuit and the waveform, we can open the model scene and see that the waveform corresponds to the circuit, and if we move, we can see that inputs and outputs are okay. So let's continue with plan B of alert2bit. I'm going to open the Quartus Prime, and we can see the VHD file into the Quartus. This is the code. This time we have the different. We have used the truth table to program this. And now we can see the RTL viewer. We can deduce that alert2bit is inside. We had 3 marks. And then we have the waveform of the circuit. As we can see, it's correct.
Okay, I'm going to explain the comparator 9-bit from SP1.4. Basically, the function of this chip is to compare if A is bigger than B, lower or equal. Okay. For example, if A is bigger, GT will be 1. That means that it's bigger. If A is lower than B, LT will be 1. That means that it's lower. And if it's equal, there will be, depending of the other inputs, other combinations. As you can see, there is a code that we took from Dixis, but it was modified to make the comparator 9-bit using only 9 comparators of 1 bit. Okay, as you can see, since chip 0 to chip 8 are all of them comparators of 1 bit with their inputs, etc. Here is the code of the comparator of 1 bit, and this is the test bench of the comparator 9-bit, and for make the model sim timing diagram. First of all, I want to check that this is well compiled, 0 errors, and if we see the RTL viewer, we can see all the chips connected with their inputs and the outputs. As you can see, they are interconnected to make the comparator 9-bit. And this is the timing diagram that shows some examples, and basically it works.
Now we are in SP14C2, and I'm going to explain how we invented the added 9-bit. First of all, I'm going to show the VHD files. The added 9-bit is composed by the triple max2, the comparator 9-bit, and the cell adder subtractor 9-bit. And later we changed this project in Quartus, we simulated, and we obtained the RTL viewer and the technology map viewer. For the waveform, we have introduced the VHD file of the test bench of the added 9-bit in Model Sim, and this is the result. As we can see, the results are correct and the circuit, it works good. So what's next? I'm going to show the added 9-bit test bench. So here we have input some numbers, in this case A and B, for example, and the input OP. So that's all.